Hey everyone, welcome to day 42. If you watched yesterday's video, we talked about data structures, but I'm sure you'll know that data structures is usually followed along with algorithms, DSA, data structures and algorithms. So today we'll do the second part, algorithms. That's also part of my assessment, my next assessment. But before we jump into algorithms, I want to explain something called as time complexity, big O notation. Here's a graph that demonstrates it. What I'm pretty much is trying to say is how quickly can something run the more data there is. So as data grows, how much longer will it take? So as you can see, O of 1 is constant time, which means that as the input size grows, the time will still remain the same. So this will be very fast the bigger the data is, whereas the other ones might not be as fast. O of log n, as you can see, is one of the more faster ones as the size increases, but it is relatively a little bit slower if the size is a bit smaller. O of log n, as input size increases, it follows along it. As the input size increases, time also increases linearly. And then O of n squared is obviously the bigger the size, the longer it will take, and it's exponential increase. So all you need to know is these just represent how fast it can run based on with the increase of data. And this is important because today we're going to be talking about algorithms such as sorting and searching and iterations. So we'll start off with some sorting algorithms. Here's the two most common ones, I guess, not common but more popular ones that come up in these tests. So we've got bubble sort. This one compares adjacent elements and swaps them if they're in the wrong order, and uses the time complexity of O n squared. As you can see, why is it O of n? Well, here we have the n, right? N is the variable, and we have two loops within each other, one loop within another loop, which means that one loop is n, second loop is n, so n times n is n squared. So the more n that we have, the longer it will take, right? And if you can read this code, it might be a little confusing, but here I can see for j in range n minus I minus 1, the minus I is here for I in range. So pretty much what I is pretty much the length of, as you can see, n is the length of the array. So imagine we have here's the first example, right? 1 2 3 4 5, so we have 5. So n equals 5 in this case because there's 5 values that we're trying to sort. So while we're in the range of 5, we'll take the first value if that value 6, if that value is bigger than the next index, which is 2, then we will do a swap. Otherwise we leave it, and then we'll keep going. We'll go to 2 if 2 and then we'll go into 2, like if 2 and 8 are, if a is bigger than if a is smaller than 2, they'll swap, and then we'll go to 8 and 4. If a is bigger than 4, they'll swap, and so on and so forth. Oops. So as you can see, 6 and 2, obviously 2 is smaller than 6, so they'll swap. And next we look at 6 and 8, they don't need to swap. 8 and 4, they do need to swap because 4 is smaller than 8, right? So they'll swap. 8 and 10, no swap needed. And now we'll go back through it again. 2, 4, 6. Oh, look here, 6 and 4 is smaller than 6, so they swap. And then we iterate again, and everything's good, and then we'll finish. We'll return. So this takes a long time, right? Because for each time we go through it, we'll need to go through it again, just in case that one of the swaps is not fully finished. So here, as you can see, we go 1 2 3 4. We go 4 passes, and yeah, it takes a while, right? O of n squared. And next we got insertion sort. it pretty much just builds a sort of a one element at a time. This is also O of n squared. So you can see, first pass, we'll take a look at the first two values, 9 and 7. If 7 is, smaller, it will move to front. Next, we'll look at 6 and compare it with the first two. If it's smaller than the first two, we'll swap. Oh well, it'll first look at 9. If it's smaller, it'll look at 7. If that's smaller, then it'll put it at the front. If not, it'll put it in between, and it'll keep going down the list. So this is also O of n squared because there's a for loop and then a while loop, so two loops within each other. So once again, O of n squared. And this will pretty much just sort the data, right? So next we got searching algorithms. This is how if you want to find something within like one of these, then how do we find it? Obviously the easiest one, linear search, O of n, which is this. So as more values there are, the longer it will take to search, right? Pretty self-explanatory. For iron range, however long, if the first index, like if we're looking for the number 10, let's take an example of this, 5 is not it, we'll move on, 6, 7, 8, 9, 10, we found it. So obviously the more data it is, the longer it will take. And then we have binary search. This one's actually will be a bit faster the more data there is, because what we're doing is, it's kind of hard to explain with the code, but and it requires a sorted list as well, right? So let's take the very end of this picture here. So if you can imagine, if we want to look for the number 7, what it does is it will take the first value here, 5, and then 17, and it will take the middle value, which is either 9 or 10. Let's say it is with 9. What I'll do is 7 between 5 and 9 or 9 and 17? And we know it's between 5 and 9, so we'll cut it in the middle, and we'll only look at 5, 6, 7, 9. And next we know that's between 5 and 9, so we'll look at 6 and 7. And then and obviously we found, oh sorry, did I say what? I already forgot what number I was looking for. Let's say we're looking for number 7, right? So 5, 17, I will take the middle, 9 or 10, but let's say 9, so take 9. Wait, I think that might be a rule, maybe it's evens, but I'm not sure. But let's say it takes 9. Actually, I want to search up, how does binary search? Okay, yeah, I just double checked, it uses the lower one, so yeah, I was right, 9 is the one we'll take. So once again, let's say we're looking for 7, we'll go 5, 17, and 9, and that's the middle. So is 17 between 5 and 9, or 9 and 17? And we know that it's between 5 and 9, so then it will look at 6 and 7, and there we have it, we found 7. So you can imagine that the bigger the size, the quicker it will be, because we can break it down more. Imagine there's only 3 numbers. We'll look at let's say we're trying to find the middle number. Let's say we have 5, 6, 7. We're trying to find 6. We'll take a look at 5 and 7. We'll know that it's between them, and we'll find 6. So that will take longer, as you can see, than just if you're just going one by one, as with like a normal linear search, right? Because you're doing all this when you can just find it with a linear search. Just go 1, 2, oh, I found it. That's why it works better with a bigger size of data. Next we have recursion. This pretty much is a function that calls itself. So here it's most commonly used in factorials. If you don't know what factorial is, it's when it's like the exclamation mark. 5 factorial is 5 times 4 times 3 times 2 times 1. So it just keeps going lower. It's pretty much n times n minus 1, and all the way till the end, until 1. So in this case, if you search up 5 exclamation mark, it should be 120, yeah, because it's 5 times 4, which is 20, and then that 20 times 3, which is 60, and that 60 times 2 is 120. So how it works here, so we have if n equals 0, obviously we return 1, because n factorial, 0 factorial is 1. Otherwise it will return n times factorial n minus 1. So as you can see, imagine we have 5 here. Obviously 5 does not equal 0, so we don't return 1, but 5 times, once again we'll have n minus 1, which is 4, so we have 4 here now. So maybe I should start with the number. So now we have 4 also does not equal 0, it does not return 1, but it returns 4 times because of 3 all the way down till it becomes 0. It becomes 1. And so when if 1 times factorial recursive n minus 1, which is 0, it will return 1, right? So now we know that this is 1 factorial. So yeah, let's start off 1. Let's start off 0. So 0, it returns 1, right? So now we know that return 1 times 0. 1 times factorial of 0 is 1. Next we have 2. So 2 times the factorial of 1, which we now know is 1, will equal 2. And then now, let's say we have 3. Now we know that 3 times the factorial of 2 is 2, so it'll be 3 times 2 is 6. And now we know that the factorial of 3 is 6. We have 4 times the factorial of 3, which we know is 6. So it's 24. And then we have 5 times the factorial of 4, which now is 24. We times that, and it's 120, right? Yeah. So yeah, that's my way to explain it, if that makes sense at all. And next, obviously we don't need to recursively do it. We can go through a normal iteration which uses loops. So here we have a variable called result when we start off with it equaling to 1, and for I in range of 2 and the number plus 1, so that it ends just at the end of the number, result times I. So we'll start off with 2, so result times 2 is 4. Once again, this used to of 5, right? So for I in range 2 and 6, so it'll go from 2 to 5. Result times 2 is 2, and then it will increase by 1, so then it will be 3. Result times 3, which is now 2 times 3 is 6, and so on until 5, which is also 120. Hope that made a bit of sense. If you guys have questions, you can ask in comments, but hope you guys learned something. Thanks for watching, and see you guys tomorrow.